So now, going back to the Mediterranean, we have a fantastic guest here with us, and he's actually a returning visitor. So our next speaker was here in the room with us last year, actually in 2019, and he decided to come back to BSidesTLV. This time, he's a speaker, and he's coming to us all the way from Greece. So give a big welcome and a big Ευχαριστώ to George. George. Thank you so much, George. The stage is yours. Here's your clicker, and here is your pointer, right there. Okay. You got it?
Great. Hold it.
Okay. George, one photo for the press.
Sure.
Thank you. All right.
Okay, so
give it up for George.
So let's get started. What we will discuss today is essentially how we can forensically detect BadUsb attacks based on behavioral vectors, not some kind of hard-coded identifier. A couple of things about me. I'm a researcher at Bitdefender, and also I study at the University of Piraeus. So let's proceed. What is the BadUsb threat model? How can someone be attacked by this vector? So every unattended computer is essentially vulnerable to an attempt. It's just plug in, plug out. That's it. Endpoint defenses may or may not interfere. Let's say that you have a rubber ducky or any other BadUsb, let's say, representative. We will discuss rubber duckies because it's the most well-known representative of the scene. And they will use a well-known malicious partial payload. This will get detected, but they may do something that will not get detected, so we're not sure about this. In our scenario, we will study credential dumping and exfiltration. Mainly, you can think of it as daily situations that can get really weird. This is just the threat model. It's quite wide. Okay, so let's do an introduction and explain the goals of this research. So everything started at the DEF CON stores. Obviously, I had to spend money somewhere, so I decided to buy the several gadgets. One of them was rubber ducky, and essentially, I also bought the manual because this is what hackers do. Oh, okay, cool. So it was a very interesting read because they explain how the rubber ducky works, and they also explain the fact that it started as a way to automate boring sysadmin stuff. So what caught my interest was the speed. They were explaining that rubber ducky is designed to work at fast speeds. It's a fast typer. So I thought, oh, hey, isn't that kind of abnormal? Like, how fast would a human type? So, as I already said, what we will focus is behavioral detection. We will try to correlate certain information, including speed, to identify whether there is a malicious attempt. And how are we going to do this? We're going to collect information from the Windows operating system. So, I think I have already covered most of this. For the scope of this research, everything we do is post-mortem, so we can assume that something has happened and we have the logs from some kind of agent running. Essentially, we need some minimum cognitive ability. We will see that we have a graph at the end of the presentation, but either a computer or an analyst would need to have some basic cognitive capabilities to understand and correlate information. So we will get deep system events, and more specifically, we will leverage event tracing for Windows and upper filters. So a couple of things about the rubber ducky. The rubber ducky is, as we said, the most common representative of the BadUsb scene. It's a fast typer. It has several cool features, and it has evolved as the time goes by. It's currently, it's under development. So it improves and improves, and it introduces several very interesting features like vendor ID spoofing. So as we said, we will focus on behavior. We will not focus on IDs of any kind. It has several interfaces. As you can see, we mentioned a couple of the features. It has some exfiltration. You can have some storage in it. We don't care that much. So what we care more is how we are gonna catch it. And we're gonna start with a journey into the operating system telemetry sources. So what is event tracing for Windows? I'm pretty sure that many of you have faced EDRs like ETW. It started as a non-security mechanism. It started mostly as a diagnostics mechanism, which evolved to be one of the greatest allies of fast defenders. So what you need to know is that it's asynchronous and it's buffer-based. And we'll see that event tracing for Windows, although it has an extreme amount of telemetry you can ingest, there are several limitations to it. It can't be actually anywhere. You can get information from the network stack, from user mode apps, from drivers, from the kernel itself. And we have the sessions, which is the glue between providers, which is those who create the events, and consumers, which is usually your agent. It's buffer-based, as we already discussed. Keep this in mind. We'll explain what it means in a few seconds. So these are the pros and cons. We got a vast amount of telemetry. We got API monitoring, which is something that was impossible due to PatchGuard. We got a pre-structured network monitoring without having to parse information from a network filtering driver. It's easy to deploy and consume. Sometimes we can also get the call stacks. Everyone who's in the EDR industry will understand that the call stacks are a gold mine for detection. So what are the cons? It's buffer-based. Buffers may flood and degrade the consumption. It's asynchronous, so we will see some examples of what this means later on, but this essentially means that events may come unordered, they may get flashed and come after a while. They won't be synchronous. They won't follow a certain order, which is actually pretty bad, and it limits what you can do with it, especially if you want to do some memory scanning or something. So there's a lot of performance overhead. It's prone to timing attacks. Due to asynchronicity mainly, you can exploit the fact that timing is inconsistent. We'll show examples right now. So what I will do now is explain to you a couple of things that happened to me. While I was experimenting, I wanted to detect via ETW memory patching and position independent code, or shellcode if you like. So essentially, we had logical issues. If we did something real fast, there was the possibility that the process would die. There would be another process created with the same PID reassigned, and we would end up with a memory scanning of a legitimate process. So we're entirely missing the detection. Memory processing issues. Maybe some module gets unloaded. Maybe something changes in memory. It's not guaranteed it will work. So there's a performance impact. ETW gives you a lot of telemetry, but also a lot of performance impact. And also, what I didn't mention earlier is that by design, events will be missed. What do I mean by that? In the previous slides, you saw a screenshot. That screenshot was from MSDN. It was essentially Microsoft admitting that events will be lost eventually. It's not designed to be foolproof. It's not designed to be 100% accurate. If you don't consume fast enough, for example, or if the event is too large, it may get dropped. It's the whole architecture. So also we can have like false positives. What do I mean by that? Event tracing for Windows will record everything that happens in the process. But imagine this. Imagine that you have an anti-exploit agent or an EDR agent. Isn't it going to do some hooking? Isn't it going to use sensitive APIs? Isn't the Windows loader going to use this kind of APIs? As much as the overhead is increased, the chances of a false positive increase as well. So let's move a little faster. So ETW is not for everything, but it actually is something that could be of use to us for this experiment. It has a lot of settings, has a lot of APIs that deal with it internally. It's quite complex. So Microsoft provided us with Krabs ETW, which is a great interface for it, and this is how essentially the ETW agent I created worked. We had some handlers in a separate namespace. We set those handlers from the manager. The manager interacts with event tracing for Windows, and we have a file logger, and we log the files. So let's move forward. These are the providers we will use. We will get image load events, process creation events, and PNP devices that are being created. So let's move to something else. What happens when you press a key on your keyboard? So a user presses the key. There is an interrupt triggered. The keyboard controller essentially handles the data. We won't go into much detail with this because they're complex, and I want us to focus on, we don't have much time, so I want us to focus on these specific 2 steps. At some point, the keyboard class driver will create an IRP, the IRP will be processed. Between these 2, there is a routine that will be called, and this is what we will hook later on. Here, the IRP is being processed, travels the driver stack, but here is the casual completion routine replacement rootkit technique. It's the most common way that you would intercept this kind of keystrokes, but we faced problems with it. We wanted something friendlier and more universal. So let's see, here's the keyboard stack. We will ignore it for the moment and focus on the ups and downs. So it's synchronous, but it's not PNP aware. The casual, when we're talking about the casual completion routine hook. And here is a different approach. We will use connect data to hook a certain routine. We will see which one later, but it's more PNP aware. We're able to use KMDF to attach to devices, etc. There's a higher success rate across machines, and it's also synchronous. But what do I mean by higher success rate across machines? If you run this one, the casual one, on a VM, it would work. If you would run it on a random physical machine, who knows, maybe you will get a blue screen. This is what I got. So we ended up going with this approach. Here's what the KMDF driver will do. The KMDF driver will essentially be registered in the registry as an upper filter driver. We will receive PNP callbacks. We will create a device. We will add our device in the context of that driver as a filter. We will create and config an IOQ, which will give us essentially a foothold to this IOCTL. This IOCTL is our gold mine, which will have this struct, connect data, and the class service routine, which will be called So actually, there will be the Keypress, there will be the ISR, and it will be queued. This routine will be queued as a DPC. Its work is to transfer data. So this is our hook. And to place our hook, we will essentially have the USB HID, which will create the ICTL, the IRP, and it will travel upwards towards our KBD class upper filter. And that's the point where we'll place the hook. Below is the point where the hook will be called. So a couple of notes. We want to avoid mistakes of the past. At some point, Microsoft had planted a keylogger for external USB devices. It was being used by Partial Empire at some point. I tried using it, didn't succeed. For some reason, maybe it was silent fixed, who knows. But it was being used as a keylogger. And also, there's another incident. HP was using a driver, which was actually a keylogger. HP planted a keylogger on your machine, and they routed the telemetry cached through ETW, so you could consume. Thank you, ZW Close 7, for this one. If you have been around Rohitab and other forums, you probably know him. Great guy. He has helped a lot, although he doesn't know it. So this is the data we will need to consider. The keystrokes and the speed of the keystrokes, the processes, the images loaded, and PNP devices. Let's see how these start working together. These are some sample logs. You will see that this name, it reads Atmel. And if you take a look at the rubber ducky, you will see that this chip has the word Atmel in it, so it starts getting fishy. You will see HID USB.sys getting loaded. What does this mean? That somebody plugged the USB device. You will see after that a partial. It's totally legit, I suppose. All these events, one after the other, it's a total coincidence. And here is what we would get in a graph, because, you know, an experienced forensic analyst would have no problem sorting out these logs, etc. But we're human. We like something more friendly towards our cognitive capabilities, and something that will help us have a clear view. So what you see here is human typing, normal human typing. What you see here, this peak means that the device was added. Here you will see suddenly a peak, some fast typing. Then you will see some partial activity. That partial was launched after the fast typing, and this is definitely a human typing in partial, right? So everyone can understand where this is going. So before you ask, can't I spread the keystrokes with sleeps? Couldn't I just evade with some proper timing? Yeah, the thing is that you would definitely expose yourself, because let's consider you're a marketing person or an HR person, and someone plugs the malicious USB, and you see partial starting typing on its own at a regular speed. Wouldn't this raise your suspicion? The least you could do is just close the window and break the attack. So this is a possible scenario I'm describing. So the gadget has to be fast, and it has to be plug in, plug out. So can the detection model be automated and made real time? Maybe have an agent that is an EDR for EDR EPP for this kind of attacks? Maybe, but you would have a lot of issues to deal with, mostly timing issues. And how would you process the models? How would you design the patterns, the malicious patterns? How would you detect certain different kinds of peaks? Like what if someone had one peak, 1 second sleep, another peak? Still malicious, still weird. You would need to somehow be able to identify that. So, we finished a bit early. This is pretty much it. I will be happy to answer any of your questions, either here or in private after the talk. So, thank you very much.
Thank you, George, or as we say in Greece, Efcharisto.
Something like that.
Something like that. Okay.